Hey crew, it's Pitt and I'm back with some more philosophy. Today we are diving back into the works of Georg Hegel. This is the science of logic. We are reading aloud and discussing as we go along the various points that are brought to light by the text. It's not the format for everyone, but people find value in it, so you are more than welcome to tag along as we continue our exploration. Before we begin, however, if you are unfamiliar with me, any of my unconventional beliefs, or if at any point in time I lose you in the terminology, there will be several playlists linked in the corner above, in the box down below, along with the original source material and the link for my book, so that you can get a better understanding of who I am and why I say the things that I do. With that being said, let us dive in and continue our exploration of the science of logic with Quantum Remark 3. Further forms associated with the qualitative determinateness of magnitude. The affirmative meaning of the infinitesimal of differential calculus is that it is the qualitative determinateness of magnitude, and regarding this determinateness, we have shown in particular that it is present in this calculus not only as a power determinateness in general, but as specifically determining the relation of a function of powers to the power of the expansion. This qualitative determinateness is also present, however, in another weaker form, so to speak, and this form, together with the use of the infinitesimal associated with it, and the meaning that the latter has in this use, will be the subject of the present remark. Before we proceed, however, it should be recalled at this juncture that the different power determinations first come in from the analytical side, that they are there merely formal and totally homogeneous, that they signify numerical magnitudes, which, as such, are not qualitatively differentiated from each other. It is in the application to spatial objects that the analytical relation fully shows itself in its qualitative determinateness, as the transition from linear to plane determinations, from the determinations of straight line to those of curves, etc. This application also brings in train that the spatial objects, which are given in the form of continuous magnitudes in accordance with their nature, will be taken discretely. The plane as an aggregate of lines, the line as an aggregate of points, etc. The sole interest of this dissolution is to determine the points and the lines into which the lines and the planes have respectively been resolved in order to be able, starting from this determination, to proceed analytically, that is, in truly arithmetical fashion. For the sought magnitude determinations, these starting points are the elements from which the function and the equation for the concrete, that is, the continuous magnitude, are to be derived. For the problems where the use of this procedure is of special interest, it is requisite that the element which is the starting point to be self-determined, in contrast with the indirect procedure which can start only with limits, and seek between them the self-determined element which is its goal. But if it is only the law of progressively determining magnitudes, without, however, ever possibly attaining the required perfect, that is, the so-called finite determination, then in both methods the result amounts to the same thing. To Kepler is ascribed the honor of first having thought of the reversal of procedure and having made the starting point. His explanation of how he understands the first preposition of Archimedes' cyclometry conveys this quite simply. Let's see if that is actually a footnote. No, it is not. There's a footnote above that we could check, but it's fine. This proposition, as we know, is that the circle is equal to a right-angled triangle, the one side of which, enclosing the right angle, equals the diameter of the circle, and the other its circumference. Since Kepler takes this proposition to mean that the periphery of the circle has as many parts as it has points, that is, infinitely many, each of which can be regarded as the base of an isosceles triangle, he thereby gives expression to the resolution of the continuous into the form of the discrete. The expression infinite which occurs here is still far removed from the meaning which it is supposed to assume in differential calculus. Now, When a determinateness of function has been found for such discrete elements, these should be summed up further as essentially elements of the continuous. But since a sum of points will not yield a line, nor a sum of lines of surface, the points are straightaway taken as already linear, just as the lines are taken as two-dimensional. But again, since linear elements ought not to be lines yet, which they would be if they were taken as a quantum, they are represented as infinitely small. The discrete is only capable of an external combination in which the moments retain the meaning of discrete units. The only transition analytically made from these units is to their sum, nor is there a geometrical transmission from point to line or from line to surface, etc. Therefore, the element which is determined as a point or a line is also given. Together also with this determination, the quality of being as point linear or as line two-dimensional, in order that their sum would indeed become, as the sum of tiny lines, a line, and as the sum of tiny planes, a plane. It is the need to get hold of this moment of qualitative transition, and for this reason to have recourse to the infinitely small, that must be regarded as the source of all the representations which, though meant to smooth out every difficulty, are themselves the greatest difficulty. But to dispense with these aids, it would have to be possible to show that contained even in the analytical procedure, which otherwise appears as mere summation, there is in fact already a multiplication. But a fresh assumption is trotted out at this juncture, which provides the basis for this application of arithmetical relations to geometrical figures. The assumption is that arithmetical multiplication is also for the geometrical determination a transition to a higher dimension, that the arithmetical multiplication of magnitudes, spatially determined as lines, is, at the same time, a promotion of the linear to the status of two-dimensional determination. 3 times 4 linear feet gives 12 linear feet, but 3 linear feet times 4 linear feet gives 12 plane feet. That is, square feet, since the unit in both factors, as discrete quanta, is the same. The multiplication of lines by lines appears at first sight to make no sense, for multiplication has to do simply with numbers. That is, it is an alteration of elements totally homogeneous with that into which they are altered. With the product, only the quantity alters. In contrast to this alteration, what has been called the multiplication of a line as such by a line, it has been named ductus lineae in lineam, like the ductus plana in planum. There is also the ductus puncti in lineam, is an alteration not merely of magnitude, but of magnitude as a qualitative determination of spatiality, of dimensionality. The transition of the line into the plane is to be understood as the self-externalization of the line, just as the self-externalization of the point is a line, and the self-externalization of the plane a whole space. This is the same as representing the motion of the point as being the line, and so on. But since motion entails time determination, it is more likely to appear in this way of representing it as merely accidental, an external alteration of state, whereas what is to be captured is the conceptual determination as expressed by self-externalization. That is, the qualitative alteration which, arithmetically, is the multiplication of unit, the point, etc., by amount, the line, etc. It may also be remarked here that in the case of the self-externalization of the plane, which would appear as a multiplying of surface by surface, there seems to emerge a difference of arithmetical and geometrical products, for that self-externalization, as ductus plani in planum, would arithmetically give a multiplication of a two-dimensional factor by another factor equally two-dimensional, and hence a product of 4 dimensions, which, however, is reduced to 3 in geometrical determination. For its part, since number has the 1 as its principal, it yields the fixed determination for the external, quantitative element, but the product of its operation is, to that extent, formal, 3 times 3, taken as a numerical determination. When it reproduces itself, yields 3 times 3 times 3 times 3. However, the same magnitude, taken as the determination of a plane, in reproducing itself is held back at 3 times 3 times 3. Because space, imagined as a moment of transcendence which starts from the point, the limit which is only abstract, attains its true limit as concrete determinateness in the third dimension, starting from the line. Okay, this is one that I actually have a little bit to add upon, right? We talked about the beginning of finite, right? That was way back in the beginning, right? Separating the infinite from the finite. The moment at which that happens is time passing. These 4 3s represents that, right? You have the 1 3 is the length, 1 is the width, 1 is the breadth, and the other 3 is the movement in space. In order to get this concrete point, you take out the movement, right? So instead of having the 4 variables, which would be 4D space, then you take it back to 3D space. But 3D space is only in the moments. It is not an actual reality, right? We live in 5D space, but we operate in 4D space physically, right? We have length, width, height, and distance, right? The relative distance from yourself. And so that would be the 4th 3. Back to the text. The difference just referred to could prove relevant in the context of free motion, where the one side, the spatial, is subject to geometrical determination according to Kepler's law, x cubed t squared, and the other side, the temporal, to arithmetical determination. How the qualitative moment, being considered here, differs from the subject of the previous remark should now be self-evident, without further comment. In the earlier remark, the qualitative moment lay in the determinateness of the powers. Here, it is the same as the infinitesimal, except only as a factor arithmetically related to product, or as point to line, line to plane, etc. The qualitative transition to be made from the discrete, into which the continuous magnitude is imagined to be resolved, to the continuous is now effected as a process of summing. But that in fact the alleged mere summation contains in itself a multiplication, therefore the transition from the linear to the two-dimensional determination appears in the simplest form in the way in which, for instance, it is shown that the area of a trapezium is equal to the product of the sum of the two opposite parallel lines and half the height. The height is represented as being only the amount of an aggregate of discrete magnitudes, which must be summed up. These magnitudes are lines laying parallel between the two parallels limiting them. They are infinitely many of them, for they are supposed to make up the plane, and yet they are lines, and therefore, in order to be two-dimensional, they must, at the same time, be posited with negation. In order to escape the difficulty of a sum of lines, supposedly wielding a plane, the lines are assumed as planes from the start, but also as infinitely thin, for they derive their determination solely from the linear character of the parallel limits of the trapezium. As parallel and bounded by the other pair of rectilinear sides of the trapezium, they can be represented as the terms of a uniformly differentiated, but in principle, indeterminate arithmetical progression, whose first and last terms are the two limiting parallels. The sum of such a series, as we know, is the product of these parallels, and half the amount of the terms. This last quantum is called amount, simply and solely with reference to the representation of infinitely many lines. It is the determinateness as the magnitude in general of a continuous, the height. It is clear that what is called a sum is at the same time a ductus lineae in lineam, the multiplying of the linear by the linear, which is, according to the above determination, the emergence of two-dimensionality. In the simplest case, now, of any rectangle in general, A, B, each of the two factors is a simple magnitude. But already in the other still elementary example of the trapezium, only one factor is simple as 1/2 of the height. The other factor is determined by a progression. It is still something linear, but its determinateness as magnitude is more complex. Insofar as it can be expressed by a series, the task of summing it is called analytical, that is, arithmetical. But the geometrical moment in it is the multiplication, and this is the qualitative moment of transition from the dimension of line to that of plane. The one factor has been taken as discrete only for the arithmetical determination of the other. By itself, like the other, is the magnitude of something linear. But the method of representing planes as sums of lines is also commonly employed where no multiplication, as such, is being performed in view of the result. This is the case when the task is to give the magnitude in the equation not as quantum, but as proportion. There is, for instance, a well-known way of showing that the area of a circle bears the same relation to the area of an ellipse, the major axis of which is the diameter of the circle, as the major axis does to the minor axis, by taking each of these areas as the sum of the ordinates pertaining to it. Each ordinate of the ellipse stands to the corresponding ordinate of the circle, as the minor axis stands to the major. Therefore, it is concluded, also, the sums of the ordinates, that is, the areas, stand in equal proportion. Those who would avoid in this connection the representation of areas or planes as a sum of lines resort to the usual, quite superfluous, ad hoc aid of making the ordinates in trapezia of infinitely small width, since the equation is only a proportion. Only one of the two linear elements of the area enters the comparison. The other element, the abscissa axis, is assumed equal in the ellipse and the circle. Therefore, as a factor of arithmetical magnitude determination equal to 1, and the proportion is, consequently, totally dependent on the relation of the one determining moment. The two dimensions are necessary to the representation of a plane. The determination of magnitude, however, as is to be given in this proportion, extends only to the one moment. Therefore, to yield to the representation, or to try to improve it by adding the representation of sum to this one moment, is in truth a failure to recognize what mathematical determinateness is all about. I do not disagree. The foregoing discussion contains also the criterion for Cavalieri's method of indivisibles referred to above, a method which the criterion also justifies, and one that does not need the recourse to the infinitely small. These indivisibles are lines when Cavalieri considers a plane, or squares and circles when he considers a pyramid or a cone, etc. He calls the baseline or base plane assumed as determined the regula. It is the constant, and with reference to a series, its first or last term. The indivisibles are regarded as parallel to it, therefore in equal determination with respect to the figure. Now, Cavalieri's general fundamental proposition is that all figures, planes as well as solid, are proportionate to all their indivisibles, those being compared with each other collectively, and if there happens to be in them some common proportion, distributively. For this purpose, he compares in figures of equal baseline and height the proportions between the lines drawn parallel to the base and equidistant from it. All such lines of a figure have one and the same determination and constitute its whole content. In this way, Cavalieri proves, for example, also the elementary proposition that parallelograms of equal height are proportional to their base. Any two lines drawn in the two figures at equal distance from the base and parallel to it are in the same proportion as the bases, and so too, therefore, are the whole figures. In fact, the lines do not constitute the content of the figure as continuous, but constitute it only insofar as they are arithmetically determinable. The linear figure is the element of the content, and through it alone must the determinateness of the latter be grasped. With this, we are led to reflect on a difference regarding where to place the determinateness of a figure, whether it is constructed like the height of the figure here, or whether it is the external limit. Insofar as it is an external limit, then one concedes that the continuity of the figure follows upon, so to speak, the equality or the proportion of the limit, e.g., the equality of congruent figures rest on the fact that the boundaries, the limiting lines, coincide. But the parallelograms of equal height and base, only this last determinateness is an external limit, the height on which the second main determination of the figures rest. The proportion of the two, and not the parallelism as such, brings the second principle of determination to the external limits. Euclid's proof of the equality of parallelograms that have the same height and base reduces them to triangles, to externally limited, continuous figures. In Cavalieri's proof, first of all concerning the proportionality of parallelograms, the limit is simply a determinateness of magnitude as such, which is explicated as taken at every pair of lines drawn at the same distance from each other in both figures. These lines, equal or in equal proportion to the base, taken collectively, yield the figures that stand in equal proportion. The image of an aggregate of lines is incompatible with the continuity of the figure. Consideration of the lines alone fully exhausts the determinateness which is at issue. Cavalieri has a standard reply to the supposed difficulty, that the representation of indivisibles requires the comparison of lines or planes which are infinite in number. He rightly points out that he is not comparing the number of such lines or planes, which we do not know. That is, it is rather an empty representation, as just remarked, introduced as prop. But only the magnitude, that is, the quantitative determinateness as such, which is equal to the space occupied by these lines. Because this space is enclosed within limits, its magnitude is also enclosed within these limits. The continuous is nothing other than the indivisibles themselves, he says. If it were anything apart from them, it would not be comparable. But it would be absurd to say that bounded continuous figures are not comparable with each other. One can see that Cavalieri's intention is to distinguish what belongs to the external existence of the continuous from that in which its determinateness lies, and which alone must be stressed when comparing it or devising theorems about it. The categories which he used for this purpose, namely the continuous as composed of or consisting in indivisibles, and the like, are admittedly not satisfactory, for implied in them is the claim to an intuition of the continuous, or, as already said, of its external existence, instead of saying that the continuous is nothing other than the indivisibles themselves. It would have been more correct to say, and consequently also self-explanatory, that the determinateness of the magnitude of the continuous is none other than that of the indivisibles themselves. Cavalieri is not comfortable with the dubious consequence drawn by the schools from the representation of the continuous as made up of indivisibles, namely, that there is a greater and smaller infinite. He expressly states further in the treatise that he is in no way forced by his methods of proof to represent the continuous as made up of indivisibles. Continuous figures only follow the proportion of the indivisibles. He says that he did not take up the aggregate of indivisibles in the way they seem to end up in the determination of the infinite, for the sake of an infinite heap of lines or planes. He took them rather because of the way they are constituted, for the specific nature of limitedness that they have in them. Nevertheless, in order to remove this stumbling block, he does not spare himself the trouble of demonstrating the main propositions of his geometry. In the seventh book, specially added for this purpose, in a way that remains free of any admixture of infinity. This way reduces the proofs to the just cited usual form of congruence of figures, that is, as we remarked, to the representation of determinateness as external spatial limit. A further remark that can be made here concerning this form of congruence is that it is no more than, so to speak, a childish aid for the intuition of the senses. In the elementary propositions concerning the triangles, two such triangles are represented side by side, on the assumption that, of the 6 parts of each, 3 in the one triangle are equal to the corresponding 3 in the other. It is shown that the two triangles are congruent, that is, that in each the remaining 3 parts are equal to the corresponding remaining 3 in the other, because, by virtue of the equality of the first 3 parts of the two triangles, cover each other. In more abstract terms, all that this equality of corresponding pairs of parts in the two triangles amounts to is that there is just one single triangle in which 3 parts are assumed as already determined, whence follows the determinateness of the remaining 3 parts. The determinateness of the one triangle is thus demonstrated to be completed with the 3 parts assumed. For the determinateness as such, the remaining 3 parts are therefore a superfluity, the superfluity of sensible existence, that is, of the intuition of continuity. When the matter is expressed in these terms, the qualitative determinateness stands out in its distinction from what is given to intuition, from the whole as continuous in itself. Congruity does not let this distinction show through. As we have observed, a new circumstance comes into play in the case of parallel lines and parallelograms. On the one hand, the equality of the triangles only, and on the other, the height of the figures from which the external limits of the latter, the sides of the parallelograms, are distinct. There is an ambiguity here as to whether in these figures, besides the determinateness of the side, which is one external limit, the base, we should take as the other external limit the other side of the parallelogram, or the height instead. In the case of 2 parallelograms that have the same base and height, but one is rectangular where the other has 2 angles sharply acute, and the opposite 2 very obtuse accordingly, intuitively the latter figure can easily appear greater than the former, for intuitively its given longer side is taken to be the determinate one, and, as Cavalieri's figurative method, the planes are compared according to the aggregate of parallel lines intersecting them. The longer side could be seen as offering the possibility of more lines than the vertical side of the rectangle does. This intuitive ambiguity, however, is no argument against Cavalieri's method, for the aggregate of parallel lines imagined in the 2 parallelograms for the purpose of comparison equally presupposes the equidistance of the lines from each other or from the base, from which it follows that the height, and not the other side of the parallelogram, is the determining moment. The situation changes again, however, when the 2 parallelograms, being compared of equal height and equal base, but do not lie on one plane and make different angles with a third plane. Here, the parallel cross sections that arise when the third plane is imagined cutting across the parallelograms in parallel motions are no longer equidistant from each other, and the two planes are unequal. Cavalieri is very careful to call attention to this difference, which he defines as one between transitus rectus and transitus obliquus of the indivisibles, thus staying at the source any superficial misunderstanding which could arise at this juncture. I remember Barrow citing in his above-mentioned work an objection of Taquet, an astute geometer who was also working at this time on new methods, bearing on precisely this subject. This Barrow is the one who also used the method of the indivisibles, though already adulterated by the assumption, which he passed on to his pupil Newton and other contemporary mathematicians, Leibniz included, that a curvilinear triangle, like the so-called characteristic triangle, and a rectilinear triangle, can be said to be equal if both are infinite. That is, very small. The difficulty raised by Taquet likewise concerns the question of which line, in the calculation of conic and spherical surfaces, should be taken as the determining factor in a method based on the application of the discrete. Taquet's objection to the method of the indivisibles is that in the calculation of conic and spheric surfaces, the triangle of the cone is represented according to this atomistic method, as made up of straight lines, parallel to the base and perpendicular to the axis, which are at the same time the radii of the circles of which the surface of the cone consists. If now this surface is defined as the sum of the circumferences, and this sum is determined from the number of the radii of the circumferences, that is, from the length of the axis and the height of the cone, then such a result would contradict the truth which Archimedes has taught and demonstrated. To this objection of Taquet, Barrow's response is that for determining the surface, it is not the axis, but the side of the triangle of the cone that must be taken as the line, the revolution of which generates the surface. And this line, not the axis, must therefore be taken as determining the magnitude for the aggregate of the circumferences. Objections or uncertainties of this kind have their origin solely in the vagueness of the representation used for the infinite aggregate of points of which the line, or of lines, of which the plane, etc., supposedly consists. It is this representation which obscures the essence of the determinateness, whether of the lines or of the planes. It was the aim of these remarks to bring attention to the affirmative determinations of the category of the infinitesimal, which, in the various uses made of this category in mathematics, remains in the background, so to speak, and to extract from them the nebulosity in which they are shrouded when the category is kept at a merely negative level of determination. In infinite series, as in Archimedes' cyclometry, the infinite means no more than that. If the law of progression of the series is known, but the so-called finite, that is, the arithmetical expression, is not given, the reduction of the arc to the straight line cannot be carried out. This incommensurability is their qualitative difference. Likewise, the qualitative difference between the discrete and the continuous contains, in general, a negative determination, which makes them appear incommensurable. It thus introduces the infinite in the sense that the continuous, which is now to be taken as discrete no longer, is supposed to have, as continuous, any quantum. The continuous, which arithmetically is to be taken as product, is thereby posited as discrete in itself. That is to say, is broken down into the elements which are its factors. Its magnitude, determinateness, lies in these factors, and they, precisely by virtue of being factors or elements, are of a lower dimension and, as the determinateness of power goes, of a lower power than the magnitude of which they are elements or factors. This difference appears arithmetically as merely quantitative, a difference of the root or the power of whatever degree they might be. However, if the expression does not go further than just the quantitative sphere of such, for example, a equals a squared or dA squared equals 2a equals 2, a squared equals 2 equals a, or for the law of gravity, T equals AT squared, it then yields the ratios 1 equals A, 2 equals A, 1 equals AT, which say nothing whatsoever as against their merely quantitative determinations. The sides would have to be held apart by the qualitative meaning differentiating them as S equals AT squared. The magnitude being thereby spoken of as a quality, as a function of the magnitude of another quality. Here, then, we are only conscious of the quantitative determinateness, and it is easy enough, in its own way, to operate with it. Nor is there anything terrible in multiplying the magnitude of a line by the magnitude of another line. However, the multiplication of these magnitudes yields at the same time the qualitative alteration of the transition of line into plane, and to this extent a negative determination comes into play. It is this determination that occasions the difficulty, a difficulty which can be resolved by an insight into its peculiarity and the simple nature of the matter, but which, when the attempt is made to eliminate it by the aid of the infinite, only degenerates unresolved into confusion. And that's going to bring us to the end of Quantum Remark 3. I piled through with a Remark 3. Hopefully I brought a little bit of enlightenment and not too much confusion to a somewhat difficult topic. I understand that I hold some unconventional beliefs, and I have a tendency to step on toes when I relay those. It is not intentional, but it is not something I apologize for. Once again, I didn't have a whole lot to add to this other than the obvious, right? I don't have a full understanding of this mathematics, and so I don't try to expound upon them beyond the point of what I do comprehend. Some of the points do make sense, and as I'm reading along, I can literally make the pieces work. So I could probably read this and follow along with no understanding of calculus and be able to do the procedures as being outlined. I could be wrong, but that does seem to be the thing, and I can literally see what's happening, right? Like, it is the measurement of the change over time. So while we took out the variable of time, the fourth dimension, we took that out. That is so that we can compare two different moments, the moments being in time. And so you have the known moment and you have the extrapolated moment, and the measuring of the distance between those two gives you the rate of change, right? That isn't the gist of calculus from what I understand, and according to this I could probably follow along. That's not to say that I am some super mathematician, but I could probably work it out. And since I can probably work it out, I'm going to assume that you can probably work it out too, because once again, I am not trained in this. All of this absolutely makes sense to me. It is perfectly logical to me, and all of the points that he makes fits with everything that we've done from part 1 up to now. And so it is a cohesive whole so far, and there's not a whole lot for me to extrapolate upon, especially about things that I don't know a whole lot about. And so, if you like what I'm doing over here, let me know down below. Give me a like, a share, a follow. Throw me a comment if you agree or disagree with anything that was said. Put it in the box down below, and if it remains respectful, it gets to remain up. If there is another work you would like to see me read or discuss, drop that in the box as well. And if you really like what I'm doing over here, hit me with that super thanks with a membership, or check out my book in the link provided in the description box down below. To the crew, thanks for hanging out. I appreciate every single minute that you are here with me, and I am praying for you every single day. Until next time, I love you. God loves you. You are perfect, whole, and complete, just the way that you are. And this has been Pitt State. Peace.